Okay, so after looking at the homeworks, it is clear that some of you really do understand the completeness relation very well. But it's also clear that there are some people who have not worked so much with the completeness relation. So I wanted to just give you a few comments because this really is such an important relation in quantum mechanics. So what is our goal here? Well, the completeness relation would say, so an integral, let's see, yeah, an integral d3, let's say, k of ket k bra k would be equal to 1. So we want to build up to an understanding of this equation. The 1 on the right-hand side, you should think about as the identity operator in Hilbert space. And on the left-hand side, well, we have the integral over ket k bra k. So why is this equal to 1? So first of all, we are, we are writing this relation in Hilbert space. Okay, so what is Hilbert space? Well, it's a vector space. So you know what that means. You know all of the axioms for a vector space. You've worked many times with vector spaces. Also, it has an inner product. Now, the reason why Hilbert space is an inner product is that if you pick up a wave function psi and you want to calculate the probability that it has some energy, for example, then you would calculate the bracket of ket psi, the state of your system, with the energy eigenket, En. So I'll label that by N. And the mod squared of that would give you a probability. So in quantum mechanics, this is always what we're calculating to compare to experiment. It's the overlap of the wave function with some state. And that's why we need an inner product, really, to make predictions. And then finally, we ask that our space is complete. Now, what does it mean for the space to be complete? Okay, so we could have a long discussion here. I'm just going to give you a very quick discussion. Just make a few statements, actually. The fact that the space is complete means if you have any convergent sequence of vectors, more technically a Cauchy sequence of vectors, then every Cauchy sequence of vectors in this space will converge to a vector inside the space. So what this is really telling you is that you can't write down a convergent sequence of vectors that converges to a vector that does not belong to the space. So there's no little holes inside the space. The reason why Hilbert came up with these axioms is that if these axioms are obeyed, so if you're working in a Hilbert space, then this is the natural generalization of working with matrices and vectors in a finite dimensional space. So you can always think about, from this point of view, you're always allowed to think about ket vectors. Let's say I work in a 2D space. So maybe this ket vector has got components A and B. Bra vectors would be row vectors. So the kets are columns, the bras are rows. So I use a transpose to go between kets and bras, and I'll assume that I'm working in a real vector space. If my vector space wasn't real, then I would have needed to complex conjugate the entries inside bra V. But I'm going to assume that I've got a real space, okay? So I'm not going to worry complex conjugating. And finally, operators you could think about as matrices. The reason why this is so useful, well, it's a crutch. So whenever you want to understand any equation in Hilbert space, you can always lean on your crutch and understand it for the finite dimensional Hilbert space. And this is actually the strategy that we're going to take now to understand the completeness relation. So you'll see this logic in action. Okay. So now let's write down a basis. So what would a basis for Hilbert space be? Well, let's take 1 to be ket vector, so column vector 1, 0, and let's take 2 to be a column vector 0, 1. So that is a basis for Hilbert space. Actually, it's an ortho, so meaning the two vectors are orthogonal, normal, meaning the two vectors are normalized. So it's an orthonormal basis. If we go ahead and we work out what is the bra basis, well, we just take a transpose. So it's 1, 0, and bra 2 would be 0, 1. Both of those being row vectors. So that works perfectly. Good. Because this is the basis, we can write any vector in this basis. In particular, we could write v in this basis. If we do that, so what is v? Well, v would be 1, 0 times by a plus 0, 1 times by b. Doesn't matter whether I write the a in front of the vector or behind the vector. Now I want to show you, well, a relation that will be nice for us. So there's a nice way to write a. If I take bra 1 and I calculate the bracket with ket v, well, this is nothing but the row vector 1, 0, a, b, and this is 1 times a, which is a, plus 0 times b, which is plus 0. So that's just a. So I can write a as the bracket of bra 1 with ket v. In a similar way, the bracket of bra 2 with ket v. So you check this. This is equal to b. So in fact, this relation over here that I have for b, I can also write it as ket 1, because that's what 1, 0 is. Then I've got the bracket of 1 and v plus ket 2 and the bracket of 2 and v. Now this equation holds for any v at all, so I can write this as ket 1 bra 1 plus ket 2 bra 2, and there is v. And if I was to multiply this bracket out as usual, I just get the top line above. Now notice v is equal to that quantity times v. So because v was any vector, I assume nothing about v, we now have a new equation. It tells us that 1 is equal to ket 1 bra 1 plus ket 2 bra 2. And this actually is the completeness relation in this two-dimensional Hilbert space that we're working in. This is the identity operator in Hilbert space. So as a matrix, it's just the identity operator. Now, the advantage of working in this 2D Hilbert space is that we can immediately check this equation. So let's check that it's true, okay? So 1, 0, well, that's ket 1, 1, 0, that's bra 1 plus. So this term over here, I have just written here explicitly in terms of the vectors. Then we've got ket 0, 1, ket 0, 1, and that term over there, I've written explicitly in terms of the vectors. And what is this equal to? Well, 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. So I just did the usual matrix multiplication. And then for the second term, 0 times 0, well, that's 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. And adding those two matrices is a trivial exercise. And indeed, I just get the identity matrix. So we've checked that the completeness relation holds. And indeed, it holds perfectly. Now, what I would like to do is, let's try to give a geometrical interpretation for the completeness relation, because then we will understand why it's true. Okay. So let me draw two axes here. I have some unit vectors along these axes. Along this axis, I've got ket1, and along this axis, I've got ket2. You know, instead of saying ket1, I could have said I hat. And instead of saying ket2, I could have said j hat, something like that. That would have been perfectly fine, and the notation would maybe have been more familiar to you. But I'm just using a different notation, okay? So I'm doing things that you know, but just in a different notation. So don't get put off by the fact that I'm using some ket vectors. Now, let's put in our vector v. So there is v. Now, I'd like to write a couple of quantities. So this length over here, that length is given by the dot product. You know, it's the projection of v along this one axis. And we know just from usual vector algebra that that's 1v. And this length over here is just the projection of vector v along the two axes. So again, just by usual vector algebra, that's the overlap of 2 and v. Now, I could say, let me turn these into vectors. So to turn this into a vector, so I want to produce a vector over there, all I need to do is multiply by the unit vector. And to turn this into a vector, all I need to do is multiply by the unit vector, okay? Now, what you can see is, and it should be quite clear to you, this vector v is nothing but the sum of this vector plus this vector. Okay, is that obvious? Use your usual tip to tail rule. There is v. Let us put this vector over there. There it is. And let us put this vector over here. There it is. So we have shown what is the geometrical meaning for this. We're breaking our vector v up into components, one along each axis, and then we're adding those different vectors to get the total vector again. That is what the completeness relation, okay, there's our completeness relation. That's what the completeness relation is saying. What this does tell you is, when you write down this completeness relation, so there it is, when you write down this completeness relation, it's quite clear from the diagram here that 1 and 2 had to be orthogonal and they had to be normalized. So when you write down this completeness relation, this must be for an orthonormal basis, okay? So that is important. But otherwise, you get the completeness relation, and this is the geometrical interpretation of the completeness relation. The next question we might want to ask is, how do we construct a complete orthonormal basis? That's the question that we'll turn to next.